Good morning. We begin lecture 19, and in today's lecture we will introduce the concept of transmultiplexers and also the topic of maximally decimated filter banks. So before that, a quick review of the concepts that we have covered in the last class so that we can build on the tools that we have for multi-rate signal processing. The general framework of a DFT filter bank. So keep this as a useful reference point. So this would be a DFT filter bank, and key elements are the fact that we have done the polyphase decomposition and have shown that the inverse DFT is the one that appears here. So we call it the DFT filter bank. We come back to this particular concept several times, but right now in this particular discussion, specific discussion, we are interested in the concept in the context of the spectral analysis, and therefore we said that if we set these polyphase components to be equal to 1, each of these polyphase components, then we actually get a filter bank where the underlying filter is a rectangular window. And it turns out, and we showed that this is pretty much what we are doing when we take the DFT or the IDFT for that matter. So basically we have a bank of filters which are giving you readings which can be interpreted as the spectral analysis of the input signal. Okay, so we went so far as to say that the basic structure of the DFT that we compute, you take a stream which is in the form of x of n plus 1, you take a block m and then you compute its DFT, and that block can be generated by means of passing the input signal through a series of advanced operators. So you get x of n plus 1 all the way to x of n plus m minus 1, that becomes your first block. You take the DFT of it, you should actually label this as the DFT coefficients, but it is another sequence, uppercase x, we call it x sub 0, x sub 1, you can think of it as the DFT coefficients. I mean, but basically it is a mapping from this input vector to the corresponding output vector. Okay. Now one element that I just want to add on to that in terms of concept is to introduce a downsampling by a factor of n. N is not the same as m. N and m are different. Basically this is a m by m DFT matrix. So this is a m by m matrix. Okay, so I am taking an m point DFT, but I am introducing a downsampling by a factor of n, and very deliberately chosen to introduce that. Okay, so my first vector is as follows, is x of n plus 1 dot 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 x of n plus m minus 1. That is my first vector. Now without ignoring the downsampling, if I just asked you what is the next instant of time, what is the vector that is being introduced, you can write down, let me use a different color. So at the next time instant, the vector for which you will be taking the DFT, if you do not do anything in this structure, will be x of n plus 1, x of n plus 2, because all of the samples would have moved by one unit. The last sample will be x of n plus m, okay, and then so on and so forth. Okay. Maybe just write one more just for so that things will become clearer when we actually do the explanation. So next one would have been x of n plus 2, x of n plus 3 dot 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 x of n plus m plus 1. Okay. Now please pay attention, if I set n equal to 1, downsampling by a factor of 1, that means it is not doing anything, right, it basically allows all the samples to go. So if I set n equal to 1, then my next vector is going to be this one. So this corresponds to n equal to 1, if this is my first vector. Now if I set n equal to 2, basically move the downsampler all the way to the left, So, that means x of n will be the first sample, then x of n plus 1 will get removed, x of n plus 2 will become the next. So, basically this becomes the n equal to 2 case. You will skip one of those vectors. Okay. Now, when does it become something of interest? I would like to look at the case where n equal to m. If I take n equal to m, then that is the non-overlapping DFT. If you remember the non-overlapping one, the next one will be x of n plus m, x of n plus m plus 1 dot 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 x of n plus 2m minus 1. Okay. So, actually the structure that we have developed is completely flexible. You can choose to have any level degree of overlap that you want, all the way from just shifting the next vector by just one sample, or by m samples, or by any other factor that you want. So, this structure, I just wanted to leave with you the thought that this structure is actually a very powerful structure. It is one that we can use quite extensively to analyze the various DFT computations that we do, and it is a very flexible structure, and it gives us all of the types of overlap. See, sometimes you want to have a 50% overlap between the successive vectors. So, which means that you would choose n equal to m by 2. M by 2 will give you 50% overlap, and of course you can have anything in between. You can have variations of that as well. Okay. Well, short time Fourier transform, the question is this a structure that is used for? So, the two things that let me just introduce a blank sheet and then write down some to answer that question. Okay. So, short time Fourier transform has the following. Short time Fourier transform, one is you must decide on your segment, length of your segment. So, length of data, okay, that is the first one that you have to decide. The second one would be the window type, because always they prefer to window the data before you compute the short time Fourier transform. So, to answer your question, what you would have to do is determine the size of the data set, which means that the m dimension has to get fixed, and then you have to apply the windowing function, be constants, and then you take the FFT. So, with this multipliers, which will be the, let us call them as W0 to Wm minus 1, that is your windowing coefficients, then you get the short time Fourier transform. So, otherwise what you are doing is just a block Fourier transform processing, right. So, good, always feel free to ask a question. So, that is the short time Fourier transform. Okay. Now, the second concept that we had mentioned in the context of multirate applications is the notion of interpolated FIR. And interpolated FIR comes from the observation that if I have some sort of a cascaded implementation, again I used the example, I repeated the example from last time so that it would be familiar. The equivalent filter can be written as H0 of Z, H1 of Z4, basically moving all the downsamplers all the way to the right and applying the noble identities. We get H2 Z power 8. We focused in on what happens when you have H of Z power L. Basically, if you were to take H2 of Z, and then if you call this as, let me just label this, if this is mod H2 E of j omega, okay. Now, this one is H2 E of j8 omega, H2 E of j8 omega, okay. I have shown only up to, I have not shown the whole thing. Okay, basically it stops at pi by 16 just to so up to pi by 16 this is what is shown. So, what we find is that when we do this Z power L, where L is some integer, you find that the spectrum gets compressed, and that gives you an advantage because that also compresses the transition band. Any practical filter will have a finite transition band, and this is a way to take advantage of the fact, but it will generate images we have to get rid of the images, and therefore the concept is that you will take advantage of the interpolation to get the sharp transitions and then introduce an additional filter. So basically we saw the example where you can design a filter H of Z as G of Z raised to the power L followed by an interpolator. Okay. So now these are called by the way this type of design are called interpolated FIR filters. Maybe I should write this as G. So the name interpolated FIR comes from the fact that if G of Z is an FIR filter, then if I do G of Z power L, that Z power L comes as if I was doing interpolation of the impulse response. So FIR comes from the basic inherent property of the filter itself. The Z power L gives me the term interpolated, so that is how we get the name interpolated FIR. But interpolated FIR by itself cannot satisfy the filter requirements. You would have to have an additional filter here to get rid of the unwanted images. So this one is the one that removes unwanted images. Okay, so maybe it's good to sort of reinforce this unwanted images. Let me just ask you to do a quick example. The example that we would like to look at in the context of the interpolated FIR technique is to do an upsampling by a factor of 50 followed by a filter that would get rid of the images H of Z. So first and foremost, if this is the requirement, I want to know what H of Z ideally should look like. A brick wall filter from minus pi over 50 to pi over 50. Okay, I have drawn it with a reasonable amount of width, but in any scale that you actually do with, if you draw it to scale, you will find that pi by 50 is a very narrow filter. Okay. So now if I cannot design ideal filters, I have to go for practical filters. So then I say that okay, no, actually what I have to design will have a finite transition. So this cutoff has to be pi by 50. This is pi by 50, but it has got a finite transition band. So the transition band also has got where the pass band ends. Let us say that I have taken it to be 7 by 8 pi by 50. If that is my specifications, please run it through some filter order estimation formula. I am sure you have done, and assume some reasonable ripple for the pass band and stop band. You will find that this will give you a very high order filter because the transition band is very sharp. Now of course that means you will have to have a lot of multipliers. On the other hand, if I were to take the design or implement the design in the following way, where I say that H of Z, I would like to take advantage Z power 25 and times I of Z. Okay, if I were to design it in this form, then the actual implementation will look like moving the interpolation, the upsampling appropriately. I will implement 50 as an upsampling by 2 and upsampling by 25. So applying the Noble identity, this becomes G of Z followed by upsampling by a factor of 25, then followed by I of Z. Okay. So we have implemented this. Now the question is there an advantage to designing it this way? Will there be fewer multipliers involved, and if so, how is the whole system going to work together? Okay. So now look at this portion of the the first part of it. So this first one should be upsampling by a factor of 2, upsampling by a factor of 2. So if I were to look at this particular signal, then it's upsampling by a factor of 2. So the G of Z should actually cut off at pi over 2, right. G of z should cut off at pi over 2, and keep in mind that we are basically going to retain the same passband relationship. So, this would be 7 by 8 times pi over 2, and of course, if you were to draw it on the other side, again you will see this is the behavior. Okay. Now, this is pi, 3 pi by 2 and pi 2 pi, and of course, you should have a corresponding image on the other side. Okay. So, the reason we are spending a little bit extra time on this is just to make sure that the advantages of interpolated FIR method are actually visible from this aspect. Now, if this is the scenario that we are trying to do, then in all likelihood we always want the signal not to be distorted. So, in all likelihood the signal was probably in this range, okay, in all likelihood. So, let us assume that that is the range, so that its signal does not get distorted. So, when I upsample by a factor of 2 and I pass it through this filter G of z, I want to remove the image. When I do the upsampling by a factor of 2, the signal will produce another image. Okay. Now, this how did this image get killed? Because the blue filter removed it. So, the blue line actually kills this portion. So, the input signal is the red spectrum, upsampled by a factor of 2, you will have an image at pi, apply a low pass filter with pi by 2 and 7 by 8 pi by 2. Again, this is a reasonable, it is not a very sharp filter, and this will kill the image here. Okay. Now, the next stage of upsampling, what does it do to my G of z? G of z becomes mapped to pi by 50, and the passband automatically gets mapped to 7 by 8 times pi by 50. So, without doing anything, I have got the desired response, and the key point is the I of z has to remove certain images. We just have to make sure where the images are coming. So, let me just do one more diagram and let us complete the discussion. So, after the upsampling by a factor of 50, there is a cutoff, there is first image at pi by 50. Where is the next image? 3 pi by 2 is the next frequency edge, that divided by 50. So, 3 pi by 50 is then going to be the next edge. So, let me just show it as this here. So, this is going to be 3 pi by 50, that is the upsampling by a factor of 25 is going to produce images and is going to produce several images. Okay. And we just want to sort of leave all of these and then go all the way to the last image. So, this has to be kept, this has to be retained, everything in between has to be killed, right. So, I of z has to be a filter that does not distort you in the pass band and gets rid of everything beyond the stop band. Okay. So, and of course, it will be, it is a low pass filter. So, basically it kills all of the other images. So, the requirements for I of z, the pass band edge is 7 by 8 times pi by 50. The stop band edge is 3 pi by 50. Again, there is a much wider transition band than the original filter that we would have had to design, and basically this would be the requirements for I of z. So, G of z power 25 times I of z will become my equivalent H of z. But because I am using it to do the upsampling, actually the interpolated FIR actually has a significant advantage, because I will implement it in this fashion, and also the filter requirements of the two filters G of z and I of z are relatively milder than the requirements on H of Z directly. So, one question. So, basically if I design it in this fashion, if I design H of Z directly, I will get a certain filter order N1. Okay. So, this comes out to be eventually a filter order of N2, this is filter order N3, G of Z power 25. So, when I add N2 plus N3, it will be greater than N1, okay, because this filter is a cascade of 2 filters and end up, but the key advantage is there are lots of zeros in this implementation, right. So, basically there are lot of 0 valued samples, and that is where we get the advantage. 0 valued samples in the impulse response. Now, we have if you do it in the polyphase in the multirate implementation, anyway you have taken advantage of that, but just to keep in mind that the computational load becomes actually lower if you go to the IFIR. The filter order itself will not be lower, but the computational load actually turns out to be lower. Okay, any questions? You have to make sure that like for example the filters G and I can be designed to be linear phase. So, it will not affect or tamper with the phase of the signal. So, usually in our filter designs, if you are able to maintain linear phase, that is the best that we can do, and so that really does not pose a problem for us. Now, just as a passing comment, where does the signal actually lie, the next copy of the signal? The next copy of the signal actually lies here, right. If you go back and look at, because the signal is preserved in the passband. So, the signal is preserved in the passband. So, the first copy of the signal is here, the second copy of the signal. So, in principle you could have designed your transition band to start here and end here. So, you could have designed it slightly wider and therefore a lower order filter as well, because ultimately what you want to kill is the signal presence of the signal. The filters are not the ultimate ones that you have to worry about, it is where the signal lies. So, as long as you have filter has got the response of that purple line, it will remove the unwanted images and you will get the desired frequency response. So, again several simple intuitive insights that you can learn from here. Hopefully if there is a chance that if you have to actually design a very narrow filter, you will not do a direct filter design, you will do an interpolated FIR design and thereby take a lot of advantages, especially if sampling rate change is going to be involved as part of the computation. Okay, so with that we would like to now introduce the new concept. By the way, the review of the cascaded integrated comb filters, basic filter is of this type. You can cascade them to get lower attenuation, but we have to keep in mind that the pass band is not flat. So, for example, the I of Z that we have designed here cannot be a cascaded integrated comb filter unless you have designed G of Z to have the pre-compensation. So, if you have designed G of Z to have the pre-compensation, then I of Z can be a multiplier-less filter and then have huge advantages. So, again this is a class of filters that are used quite extensively in ASIC design, because primarily because they are multiplier-less filters.